The universe is 13.8 billion years old. Our civilization has existed for roughly 10,000 years. That means the cosmos had 13.799 billion years of history before we ever looked up at the stars. If another civilization emerged just 1% earlier in cosmic time, they would have a 130 million year head start on us. That is enough time to cross the entire Milky Way at a fraction of the speed of light. Not through wormholes, not through warp drives, through patience, through slow, grinding, sublight travel across the crushing distances between stars. No known law of physics prevents it. The question is not whether interstellar travel is possible. The question is whether something ancient and patient launched itself toward the stars long before Earth existed. If you enjoy journeys that challenge everything you thought you knew about our place in the cosmos, do me a favor and hit that like button and subscribe. It genuinely helps the channel grow and lets me keep making content like this for you. Make yourself comfortable. Let's begin. $13.8 billion years. That is the confirmed age of our universe, measured with extraordinary precision by the European Space Agency's Planck satellite using temperature fluctuations in the cosmic microwave background radiation. Not an estimate, not a rough guess. A number backed by decades of independent measurements converging on the same answer from multiple branches of astrophysics, cosmology, and nuclear physics. 13.8 billion years since the first light broke free from a cooling plasma, and space became transparent for the very first time. Now hold that number in your mind and compare it with another one. 4.6 billion years. That is the age of our solar system. The sun ignited from a collapsing cloud of gas and dust. The planets coalesced from a spinning protoplanetary disk, and Earth began assembling itself from violent collisions between rocky debris roughly 4.6 billion years ago. This means the universe existed for over 9 billion years before our star even switched on. 9 billion years of cosmic evolution, star formation, supernova explosions, planetary assembly, chemical enrichment, and gravitational sculpting occurred before a single photon of sunlight ever warmed the surface of our world. That gap is not a footnote in cosmic history, it is the foundation of everything that follows in this story. Because if the universe had 9 billion years of running time before Earth joined the show, the question we need to ask is brutally simple and profoundly unsettling. What was happening during all that time? What kinds of stars were forming? What kinds of planets were assembling around those stars? And most importantly, could something intelligent have emerged during those 9 billion years, looked up at its own alien night sky, and decided to reach for the stars long before our planet even existed as a possibility? To understand why this question carries genuine scientific weight, you need to understand how stars are born and how planets become possible in the first place. The very first stars in the universe were nothing like our Sun. They formed roughly 100 to 200 million years after the Big Bang, from clouds of almost pure hydrogen and helium, the only elements that existed in significant quantities at that time. These primordial giants, classified by astronomers as population 3 stars, were enormous and unstable. Some contained several hundred solar masses packed into thermonuclear furnaces so violent they burned through their fuel in just a few million years. By comparison, our Sun has been steadily burning hydrogen for 4.6 billion years and has enough fuel to continue for roughly another 5 billion. When these first-generation stars died, they died in the most spectacular fashion the universe has ever produced. Supernovae and hypernovae ripped these stellar giants apart, blasting their outer layers into the surrounding interstellar medium at thousands of kilometers per second. But their deaths were not merely destructive. They were creative. Inside the crushing pressures of their collapsing cores, nuclear fusion had built heavier elements that had never existed before in the history of the cosmos. Carbon, oxygen, nitrogen, silicon, magnesium, iron. The entire periodic table of elements heavier than helium owes its existence to the deaths of earlier stars. Every atom of calcium in your bones, every atom of iron in your blood, every atom of oxygen you are breathing right now was forged in the heart of a star that exploded before our sun was born. This process is called stellar nucleosynthesis, and it changed the chemistry of the universe permanently and irreversibly. The gas clouds that formed the next generation of stars, classified as population 2, were no longer pristine hydrogen and helium. They contained traces of heavier elements seeded by the deaths of their predecessors. These heavier elements, which astronomers collectively refer to as metals, regardless of their actual chemical identity, made something new possible. They allowed the formation of solid particles in protoplanetary disks, dust grains, pebbles, rocks, boulders, eventually rocky planets capable of retaining liquid water on their surfaces. Here is where the timeline becomes staggering, and where the implications begin to cascade. By the time the universe was roughly 3 to 4 billion years old, the Milky Way and galaxies like it were already well into their assembly phase. Stars were forming at prodigious rates, far higher than the current star formation rate in our galaxy today. Heavy element enrichment was accelerating with every generation of stellar death and rebirth, each supernova seeding the interstellar medium with more of the chemical ingredients needed for rocky planet formation. By 4 to 5 billion years after the Big Bang, which corresponds to roughly 8 to 9 billion years before our sun even formed, there were already billions of star systems in our galaxy alone that possessed the chemical toolkit necessary to build Earth-like worlds. Think carefully about what that means. Billions of stars with the right chemistry to produce rocky planets sitting in habitable zones existed when the universe was less than half its current age. If even a tiny fraction of those systems produced worlds where liquid water could persist on the surface, where volcanic activity recycled nutrients, where magnetic fields shielded atmospheres from stellar radiation, then the fundamental conditions for life as we understand it existed billions of years before our solar system was even a theoretical possibility. This is not speculation. Scientists have confirmed this timeline through direct observation. The Kepler Space Telescope, which operated from 2009 to 2018, discovered thousands of exoplanets orbiting stars of various ages, including stars far older than our Sun. One of the most remarkable discoveries was Kepler 444, a system containing at least 5 rocky planets orbiting a star that is 11.2 billion years old. That star formed when the universe was only roughly 2.6 billion years old. Its planets have existed for more than twice as long as Earth, more than twice as long for geology to reshape surfaces, more than twice as long for atmospheric chemistry to evolve, more than twice as long for whatever processes lead to molecular complexity and potentially biology to unfold across deep time. And Kepler 444 is not a singular anomaly. Comprehensive surveys of exoplanet populations reveal that rocky planets are common around older stars across a wide range of metallicities. The galaxy did not wait patiently for our sun to begin producing worlds. It was building them relentlessly, generation after generation, cycle after cycle, for billions of years before we arrived on the scene. We are latecomers to a process that was already ancient when our corner of space began to take shape. Now let us quantify what a civilizational head start actually means in practical terms, because the numbers involved transform an abstract cosmic fact into something deeply confrontational. Humans have existed in our anatomically modern form for roughly 300,000 years. Our entire recorded civilization, from the first crude agricultural settlements to the International Space Station, fits within a window of about 10,000 years. The gap between the Wright brothers achieving powered flight at Kitty Hawk and Neil Armstrong stepping onto the lunar surface was 66 years, a single human lifetime. The gap between the first radio transmission by Guglielmo Marconi and the launch of the Voyager probes toward the outer solar system was less than 80 years. In under 2 centuries, our species went from horse-drawn carriages to spacecraft, leaving the solar system entirely. That pace of technological acceleration is breathtaking by any measure, but it represents an almost invisibly thin sliver of cosmic time. If the universe's entire 13.8 billion year history were compressed into a single book of 1,000 pages, with each page representing 13.8 million years, all of recorded human civilization would not occupy the final chapter. It would not fill the final paragraph. It would not even constitute the final sentence. It would be the final period on the final sentence of the final page, a single dot of ink at the very end of a very long story that had been telling itself for 1,000 pages before that dot appeared. Now imagine a civilization that began writing its own story just 1 million years before ours. 1 million years sounds like an eternity by human standards, but it is nothing in cosmic terms. It is less than 1/100th of 1% of the universe's total age. It is a rounding error on the timescale of stellar evolution, a blip so small it would be invisible on any graph of cosmic history. But for a technological species experiencing exponential growth in capability and knowledge, 1 million years is an ocean of developmental time so vast it defies comprehension. Consider the comparison directly. If humanity progressed from sharpened stones to nuclear reactors and microprocessors in approximately 10,000 years, what could a civilization accomplish with 100 times that duration? What about a civilization with a 10 million year head start, 1,000 times our developmental window? What about 100 million years, 10,000 times our window? At these timescales, even the most conservative assumptions about technological progress produce outcomes that would appear indistinguishable from magic to our current understanding. And remember, we are not even discussing the oldest possible civilizations. We are discussing modest head starts. A civilization that arose around one of those ancient stars that formed 8 or 9 billion years ago, stars we have confirmed exist and confirmed had the chemistry for rocky planets, would have had not millions but potentially billions of years of developmental time. The numbers are so large they stop feeling real, but they are real. The stars are real. The planets are real. The chemistry is confirmed, and the time is measured, verified, and beyond reasonable dispute. This brings us from cosmic timescales to our actual galactic neighborhood, because the theoretical possibility of ancient civilizations means nothing if there are no plausible destinations within reach. If habitable worlds were vanishingly rare or separated by distances so extreme that no conceivable amount of time could bridge them, the entire premise would collapse under its own weight. But that is not what the observational data shows, not even remotely close. The nearest star system to our Sun is Alpha Centauri, a triple star system located 4.37 light-years from Earth. Within that system sits Proxima Centauri, a small red dwarf star gravitationally bound to the larger binary pair of Alpha Centauri A and B, but orbiting at a considerable distance from them. In August of 2016, astronomers at the European Southern Observatory confirmed the existence of Proxima Centauri b, a rocky exoplanet orbiting within the habitable zone of its host star. The planet has a minimum mass of approximately 1.27 Earth masses, placing it firmly in the rocky planet category. It orbits close to its star, completing one full revolution in just 11.2 Earth days. But because Proxima Centauri is a dim red dwarf, emitting far less radiation than our Sun, its habitable zone lies much closer in than the habitable zone of a solar-type star. Proxima Centauri b is not confirmed to be habitable. Red dwarf stars are known to produce intense stellar flares that could strip planetary atmospheres over time. Tidal locking, where one hemisphere perpetually faces the star while the other faces away, may create extreme temperature differences that challenge atmospheric stability. But the planet exists. It is rocky. It orbits in the temperature range where liquid water is theoretically possible, and it is practically next door by galactic standards. 4.24 light-years. That is the distance to the nearest known potentially habitable world, our cosmic neighbour. Move outward from Proxima Centauri, and the options multiply rapidly. Barnard's star, approximately 6 light-years from Earth, is an ancient red dwarf with at least one candidate exoplanet that remains under investigation by astronomers. Ross 128, roughly 11 light-years away, hosts a rocky planet called Ross 128b that receives only about 1.38 times the stellar radiation Earth receives from the Sun, making it one of the most temperate nearby exoplanets currently known. Tau Ceti, approximately 12 light-years from our solar system, shows evidence of multiple planetary candidates, with at least 2 orbiting near the conservative habitable zone boundaries. Epsilon Eridani, about 10.5 light-years away, hosts a confirmed gas giant and shows intriguing signs of additional planetary companions that remain under investigation. These are just the systems within a roughly 15 light-year radius of Earth, a tiny bubble of space in a galaxy 100,000 light-years across. Expand the search volume to 50 light-years and the number of known exoplanet hosting stars grows into the hundreds. Expand it to 100 light-years and you are dealing with thousands of confirmed planetary systems. Expand the calculation to the entire galaxy and the numbers become genuinely overwhelming. NASA's Exoplanet Archive catalogues over 5,500 confirmed exoplanets as of recent counts, with thousands of additional candidates awaiting verification. The Kepler mission alone revealed that planetary systems are the norm, rather than the exception among stars in our galaxy. Statistical analyses of Kepler survey data suggest that roughly 20% of Sun-like stars host at least one rocky planet in their habitable zone. Apply that conservative ratio to the estimated 400 billion stars in the Milky Way, and you arrive at a staggering figure. Tens of billions of potentially habitable rocky worlds scattered across our single galaxy. Let that number settle for a moment. Tens of billions. Not millions, not thousands. Tens of billions of rocky planets sitting at the right distance from their parent stars for liquid water to theoretically exist on their surfaces. Distributed across a galaxy that has been producing such worlds for over 10 billion years. Some of those planets are young, recently formed, still cooling, still being pummeled by late heavy bombardment debris. But many of them are ancient, billions of years older than Earth. They have had far more time for geological cycling, far more time for atmospheric evolution and chemical complexity, far more time for whatever processes might lead toward biological activity and eventually toward intelligence. The TRAPPIST-1 system illustrates this point with remarkable clarity. Located approximately 39 light-years from Earth, this ultra-cool red dwarf star hosts 7 confirmed rocky planets, at least 3 of which orbit within the habitable zone. The system was discovered in 2017 and immediately became one of the most intensely studied exoplanetary systems in the history of astronomy. The planets are tightly packed in close orbits, with periods ranging from 1.5 to 18.8 Earth days. Several of them could potentially support surface liquid water, depending on atmospheric composition, thickness, and greenhouse effects. TRAPPIST-1 is approximately 7.6 billion years old. That makes it 3 billion years older than our entire solar system. 3 billion additional years of planetary evolution, atmospheric chemistry, surface weathering, and potential biological development. If something intelligent arose in the TRAPPIST-1 system, even a small fraction of that 3 billion year head start ago, that civilization would have had an almost incomprehensible developmental advantage over humanity. A million-year-old civilization there would still have emerged long before the first hominids walked upright on Earth. And TRAPPIST-1 is just one system among billions. The Milky Way is a vast rotating disk, roughly 100,000 light-years in diameter, containing an estimated 400 billion stars organized into sweeping spiral arms, a dense central bulge, and an extended stellar halo. Within this enormous structure, habitable zone planets are not rare curiosities. They are commonplace. Every survey that probes deeper and examines more stars finds more of them. The galaxy is saturated with potential destinations, potential homes, potential cradles for life and intelligence. Consider the broader distribution. The galactic habitable zone, a concept developed by astronomers to identify regions of the Milky Way most conducive to complex life, extends through much of the galactic disk, Stars in this zone have sufficient metallicity for rocky planet formation, are far enough from the galactic center to avoid intense radiation from the supermassive black hole and frequent supernova activity, and are close enough to benefit from the higher metallicity of the inner disk. Our Sun sits comfortably within this zone, but so do hundreds of billions of other stars, many of them significantly older. Imagine walking through a vast airport terminal with a departures board stretching across the entire wall. Each line on that board represents a star with at least one confirmed or candidate habitable zone planet. The board does not show dozens of departures. It does not show hundreds. It shows billions of potential gates, billions of potential destinations, stretching farther than you can see in either direction. Some of those gates have been open for billions of years longer than ours. Some of those destinations have been waiting for visitors since before our Sun was a cloud of cold gas drifting through a spiral arm. But potential is not certainty, and this distinction matters enormously. Having a planet in the habitable zone does not guarantee liquid water. Having liquid water does not guarantee the emergence of life. Having microbial life does not guarantee the evolution of complex multicellular organisms. Having complex life does not guarantee intelligence. And having intelligence does not guarantee the development of technology capable of reaching the stars. Each step along this chain involves profound uncertainties that we cannot yet quantify with confidence, because we have exactly one confirmed example of the full sequence: Earth, us. One single data point in a galaxy of tens of billions of possibilities. What we can say with genuine scientific confidence is that the raw ingredients are abundant beyond measure. The time was available in staggering quantities long before we arrived. The galaxy is filled to overflowing with plausible destinations sitting at finite, measurable distances from one another, and the chemical and physical prerequisites for rocky planet formation were satisfied billions of years before our Sun ignited. Astronomers measure stellar metallicity across different populations and regions of the Milky Way to track when habitable planet formation became chemically viable. Studies comparing metal-poor halo stars with metal-rich disk stars show a clear progression. The galactic disk reached approximately solar-level metallicity in many regions roughly 6 to 8 billion years ago. Some inner disk regions achieved sufficient enrichment even earlier. This confirms that Earth-like planet formation was chemically feasible across large swaths of the Milky Way several billion years before our own solar system assembled from its natal cloud. The implications cascade through every layer of the question. If rocky planets were forming in habitable zones 6 or 7 billion years before Earth, and if even a vanishingly small fraction of those planets developed stable surfaces with liquid water and atmospheric protection, then biology could have emerged in the Milky Way billions of years before the first microbes appeared in Earth's primordial oceans. Earth's oldest confirmed microfossils date to roughly 3.5 billion years ago, suggesting that life appeared relatively quickly once surface conditions allowed it. If that pattern holds elsewhere, if life tends to emerge promptly when conditions permit, then living worlds could have existed in our galaxy when the universe was barely a third of its current age. Now extend the timeline further forward. Life on Earth required approximately 3.5 billion years to progress from the earliest single-celled organisms to a species capable of building radio telescopes and launching spacecraft. That is an immensely long time by human experiential standards, but it is substantially less than the age gap between Earth and many older planetary systems confirmed to exist in the galaxy. A planet that formed 10 billion years ago would have had 3.5 billion years to develop complex life and still retain over 2 billion years of additional evolutionary runway beyond where Earth currently stands. 2 billion years of additional time during which intelligence, technology, industrial capability, and interstellar ambition could have developed and matured in ways we cannot predict or model with any confidence. We cannot know what happened on those ancient worlds. We have no data, no intercepted signals, no confirmed evidence of extraterrestrial intelligence anywhere in the galaxy or beyond. That absence is real and scientifically important, and we will confront it directly and honestly later in this story. But the timeline is equally real. The chemistry is confirmed through spectroscopic observation. The planets have been detected and catalogued. And the mathematics does not bend to human preference or discomfort. The galaxy was building habitable worlds billions of years before Earth existed. Some of those worlds sat in stable orbits around long-lived main sequence stars, capable of providing consistent energy output for many billions of years. Some of them almost certainly developed complex surface chemistry. Whether any of them crossed the threshold into biology, then into complexity, then into intelligence, then into technology, remains unknown. But the window of opportunity was not narrow. It was staggeringly, overwhelmingly wide, billions of years wide, tens of billions of planets wide, an hourglass with so much sand already fallen through that the pile at the bottom dwarfs what remains above. Imagine standing before the skyline of an enormous city at night. Lights glitter in every direction as far as you can see, stretching to every horizon. Towers and structures of every size crowd together, some ancient and weathered, others newer and gleaming. Now imagine being told that this city has been here for 9 billion years, growing, expanding, building new structures and welcoming new residents generation after generation for almost twice as long as the Earth has existed. You just arrived. You have been standing here for 10,000 years out of 9 billion. You look out at the endless lights and you wonder whether anyone else lives in this city. The lights suggest they might. The sheer age of the city and its infrastructure suggests that residents almost certainly came before you, but you cannot see anyone from your balcony. Not yet. The city is too large and you have been here for too short a time to have explored even the nearest block. That is our situation in the Milky Way. The galaxy is the city. The lights are stars with habitable zone planets. The 9 billion years of prior construction is the staggering cosmic timeline before Earth assembled from its protoplanetary disk. And we are the newcomers, standing on a single balcony in a single building, squinting into the vast distance, wondering whether we are alone in a metropolis that was thriving long before we opened our front door for the first time. The exoplanet data gives us a clear and resounding answer to the first critical question in our logical chain. Are there places to go? Are there destinations worth reaching? Yes. Overwhelmingly, emphatically, yes. The galaxy contains tens of billions of potentially habitable worlds, many of them significantly older than Earth, distributed across distances that are immense but finite and precisely measurable. The raw material for interstellar civilizations exists in staggering abundance. The prerequisite conditions were met billions of years before humanity took its first breath. But destinations alone mean nothing if the journey between them is physically impossible, and this is exactly where the conversation usually stalls, where human intuition builds a wall that feels impassable. People hear the distances involved, 40 trillion kilometers to the nearest star system. They hear the travel times at current spacecraft velocities, tens of thousands of years, hundreds of thousands of years, and they conclude that interstellar travel is effectively impossible, that the stars are simply too far apart, that the void between them is too wide, too cold, too empty, that the journey is too long for anyone or anything to survive. That conclusion feels intuitive, it feels reasonable, it feels obvious, and it is wrong. Not because the distances are exaggerated, they are accurate to within a fraction of a percent. Not because some secret undiscovered technology makes the trip quick and easy. No such technology exists within known physics. The conclusion is wrong because it evaluates cosmic distances against the yardstick of human timescales instead of cosmic ones. And on cosmic timescales, the distances between neighbouring star systems are not impenetrable barriers. They are commutes, long commutes, tedious, grinding, multi-generational commutes. But crossable commutes for any civilization patient enough to endure them and persistent enough to attempt them. What those commutes actually look like, how fast a realistic spacecraft could travel using propulsion methods that do not violate any known law of physics, and exactly how many years the journey would take to reach specific nearby star systems at various achievable velocities is where we turn next. because the numbers are not what most people assume. They are large. But they are not infinite. And in a universe that has been running for nearly 14 billion years, even a very large number can be frighteningly, disturbingly small. The speed of light is the fastest anything can travel in our universe. 300,000 kilometers per second, 1,080,000,000 kilometers per hour. A photon leaving the surface of the Sun reaches Earth in 8 minutes and 20 seconds, crosses the orbit of Jupiter in roughly 43 minutes, and passes beyond the outermost planets of our solar system within a few hours. At this ultimate cosmic velocity, light is fast enough to circumnavigate the Earth 7.5 times in a single second. Nothing that carries mass or information can exceed this speed. It is not merely a technological limitation that clever engineering might someday overcome. It is a fundamental property of space-time itself, woven into the fabric of reality by the laws of Einstein's special relativity. You cannot outrun light, any more than you can travel north of the North Pole. The concept itself becomes meaningless. This speed limit defines everything about interstellar travel. Every propulsion system, every mission architecture, every journey plan must operate beneath this absolute ceiling. And when you apply that ceiling to the distances between stars, the results initially feel devastating. Because even at light speed, the nearest star system to Earth requires over 4 years to reach. The TRAPPIST-1 system, with its tantalizing array of 7 rocky planets, requires 39 years. A star on the far side of the Milky Way requires 100,000 years. These are the travel times at the fastest speed the universe permits, and no realistic spacecraft will ever come close to achieving light speed. The energy requirements scale exponentially as you approach that barrier, reaching infinity at the limit itself. A spacecraft carrying meaningful payload to even 50% of light speed would require more energy than entire civilizations currently produce. So let us abandon the fantasy of light speed travel and confront what is actually achievable. Let us work with the speeds that known physics and plausible engineering can deliver. Speeds that are fast by any human standard but glacially slow compared to the distances involved. And let us see whether interstellar travel remains possible under those honest, conservative, physically realistic constraints. Start with where we are right now. The fastest human-made object currently in operation is the Parker Solar Probe, which during its closest approaches to the Sun reaches speeds of approximately 195 kilometers per second. That is roughly 700,000 kilometers per hour, or about 0.065% of the speed of light. Staggeringly fast by terrestrial standards. Faster than any bullet, any missile, any vehicle humans have ever constructed for any other purpose. At this speed, you could travel from New York to Los Angeles in approximately 20 seconds. But point that velocity toward Proxima Centauri, 4.24 light-years away, and the arithmetic delivers a sobering answer. At 195 kilometers per second, reaching Proxima Centauri would require approximately 6,500 years. That is longer than all of recorded human civilization. Longer than the time separating us from the construction of the first Egyptian pyramids. Every dynasty, every empire, every technological revolution humanity has experienced fits comfortably within the travel time to our single nearest neighbouring star at the fastest speed we have currently achieved. The Voyager 1 spacecraft, launched in 1977 and now the most distant human-made object from Earth, travels at roughly 17 kilometers per second relative to the Sun. At that velocity, reaching Proxima Centauri would require approximately 73,000 years. Voyager has been travelling for nearly 5 decades and has covered roughly 24 billion kilometers. That sounds impressive until you realise that the distance to Proxima Centauri is approximately 40 trillion kilometers. Voyager's entire epic journey across nearly 50 years of flight represents less than 1/1600th of the distance to the nearest star. It is a single footstep at the beginning of a cross-country hike that stretches across continents. These numbers are the reason most people instinctively dismiss interstellar travel as impossible. When your fastest existing technology requires thousands or tens of thousands of years to reach the nearest destination, the venture feels hopeless. But this reaction is based on a critical error in framing. It assumes that current spacecraft speeds represent the ceiling of what is achievable. They do not. Not remotely. Current spacecraft speeds reflect the specific engineering choices and budgetary constraints of early-stage spacefaring civilizations. They do not reflect the limits of physics. The gap between what we have built and what physics permits is enormous, and closing even a fraction of that gap transforms the interstellar equation entirely. Let us walk through the plausible speed regimes, starting conservative and scaling upward, examining what each velocity means for travel times to real nearby star systems. At 1% of the speed of light, designated 0.01 c in physics notation, a spacecraft travels at approximately 3,000 kilometers per second. This is roughly 15 times faster than the Parker Solar Probe, and 176 times faster than Voyager 1. It is fast, genuinely fast, but it does not require exotic physics or undiscovered energy sources. It requires significant engineering advancement applied to propulsion concepts that already exist in theoretical form. At 0.01 c, the travel times to nearby stars become long but no longer absurd across cosmic timescales. Proxima Centauri, at 4.24 light-years, requires approximately 424 years. Barnard's star at 6 light-years requires roughly 600 years. Epsilon Eridani, at 10.5 light-years, requires approximately 1,050 years. Tau Ceti, at 12 light-years, requires roughly 1,200 years. The TRAPPIST-1 system at 39 light-years requires approximately 3,900 years. These are substantial durations. No individual human could survive any of them. But they are not beyond the reach of engineered systems designed for persistence across centuries. A journey of 400 years to Proxima Centauri is shorter than the time separating us from the European Renaissance. A journey of 1,000 years to Epsilon Eridani is shorter than the gap between modern civilization and the Viking Age. These are timescales that human institutions have already survived in various forms, though admittedly not in the vacuum of interstellar space aboard a spacecraft. The point is that centuries and low millennia are not incomprehensible durations. They are long, they are challenging, but they are not infinite. Now scale up to 5% of the speed of light, 0.05 c, approximately 15,000 kilometers per second. At this velocity, the travel times compress dramatically. Proxima Centauri falls to roughly 85 years, Barnard's star to 120 years, Epsilon Eridani to 210 years, Tau Ceti to 240 years, TRAPPIST-1 to 780 years. At 5% light speed, the nearest star systems become reachable within a single long human lifetime, or just beyond it. The more distant targets within 50 light-years fall within a range of centuries rather than millennia. These are durations that, while still immense by the standards of a single human career, become plausible for multi-generational projects or for travelers who are not constrained by biological aging. At 10% of the speed of light, 0.1 c, approximately 30,000 kilometers per second, the numbers become genuinely striking. Proxima Centauri requires roughly 42 years. Barnard's star, approximately 60 years. Epsilon Eridani, 105 years. Tau Ceti, 120 years. TRAPPIST-1, approximately 390 years. At this velocity, the nearest star is reachable well within a human lifetime. A crew that departed Earth at age 30 could arrive at Proxima Centauri at age 72. This is not comfortable. It is not quick, but it is achievable without any violation of known physics, without any exotic technology, without any modification to our understanding of space-time or relativity. It simply requires a spacecraft capable of sustained acceleration to 10% of light speed and sufficient shielding and life support to protect its passengers across 4 decades of flight. These velocity targets are not arbitrary fantasies. They correspond to specific propulsion concepts that have been studied in serious engineering and physics literature. concepts grounded entirely in known physical principles, even if they remain beyond our current engineering capacity. Solar sails represent the simplest and most elegant propulsion concept that requires no onboard fuel whatsoever. A solar sail is exactly what the name implies. A vast, ultra-thin, reflective membrane that captures momentum from photons emitted by the sun or by a powerful directed laser. The Japanese space agency JAXA successfully demonstrated solar sail propulsion in 2010 with the Icaros spacecraft, which deployed a 14-meter sail and achieved measurable acceleration from solar radiation pressure in interplanetary space. Icaros proved the fundamental principle works. The question is one of scale and power. The Breakthrough Starshot initiative, announced in 2016, with funding from investor Yuri Milner and support from the late physicist Stephen Hawking, proposed using an array of ground-based lasers to accelerate a gram-scale spacecraft fitted with a light sail to approximately 20% of the speed of light. At that velocity, a tiny probe could reach Proxima Centauri in roughly 21 years. The engineering challenges are formidable. The laser array would need to deliver approximately 100 gigawatts of focused power for several minutes. The sail would need to survive intense radiation pressure without melting or deforming. The probe itself would need to be miniaturized to a scale barely larger than a computer chip, while carrying cameras, communication equipment, and navigation systems. None of these challenges bump against the boundaries of what nature permits. They are engineering problems, extraordinarily difficult engineering problems, but the distinction matters profoundly. A physics violation means something cannot be done regardless of technological advancement. An engineering challenge means something cannot be done yet with current capabilities but might become achievable with sufficient development. Breakthrough Starshot operates entirely within the boundaries of confirmed physical law. Nuclear pulse propulsion offers another path grounded in known physics, though it carries obvious political and environmental complications. The concept originated with Project Orion, studied by physicists including Freeman Dyson at General Atomics during the late 1950s and early 1960s. The basic idea is straightforward if dramatic. A spacecraft carries a supply of small nuclear devices. It ejects them one at a time behind the vehicle, detonates them at a calculated distance, and rides the resulting plasma shockwave forward. Each detonation provides an enormous impulse. The cumulative effect of thousands of sequential detonations could theoretically accelerate a massive spacecraft, not a gram-scale probe but a vessel weighing thousands of tons, to velocities between 3 and 5% of the speed of light. Project Orion was never built for political and treaty reasons, not for physics reasons. The Partial Nuclear Test Ban Treaty of 1963 effectively ended the program by prohibiting nuclear detonations in space, but the physics was sound. Dyson himself calculated that an Orion-type vehicle could reach Alpha Centauri in approximately 130 years, carrying a payload large enough to support a human crew or a substantial robotic science mission. The concept remains one of the most thoroughly studied interstellar propulsion architectures in the engineering literature. Fusion propulsion represents a more refined approach. Instead of nuclear explosions, a fusion drive would use controlled thermonuclear reactions to heat and expel propellant at extraordinarily high exhaust velocities. The British Interplanetary Society's Project Daedalus, studied in the 1970s, proposed an uncrewed interstellar probe powered by inertial confinement fusion using pellets of deuterium and helium-3. The design called for a two-stage vehicle that would accelerate to approximately 12% of light speed, reaching Barnard's star in roughly 50 years. A successor study called Project Icarus, initiated in 2009, revisited and updated the Daedalus concept with modern engineering and physics knowledge. Again, the critical point is not that these vehicles have been built, they have not. The critical point is that their designs do not require undiscovered physics. They require mastery of fusion engineering, advanced materials science, and manufacturing capabilities beyond our current level. For a civilization even a few centuries more advanced than ours, these represent solvable problems. For a civilization thousands or millions of years ahead, they may represent trivially solvable problems, the equivalent of Stone Age humans contemplating whether it is possible to cross a river. Now, here is where the frame shifts entirely, and the true argument takes hold. Everything discussed so far evaluates interstellar travel from the perspective of a young civilization like ours. We look at the distances and wince. We look at the travel times and despair. We calculate the energy requirements and conclude the task is too hard. But we are making a fundamental error of perspective. We are measuring cosmic distances with a human ruler and finding them wanting. The universe does not use human rulers. Recall the central fact we started with. The Milky Way galaxy is approximately 13 billion years old. Stars have been forming, living, dying, and enriching the interstellar medium with heavy elements for almost the entire history of the cosmos. Habitable planets have existed for billions of years before Earth. Civilizations that arose even modestly earlier than ours on the cosmic timescale have had developmental windows measured in millions or billions of years. Now place the travel times we just calculated against that backdrop and watch the perspective transform completely. A journey to Proxima Centauri at 1% of light speed takes 424 years. That is less than 1/30 millionth of the age of the galaxy. If the galaxy's history were a 24-hour clock, this journey would occupy less than 3/1000ths of a second. A blink so brief it would be invisible to any observer tracking cosmic time. A journey to the TRAPPIST-1 system at 1% of light speed takes approximately 3,900 years. That sounds like an eternity to a human being. But set it against 13 billion years of galactic history, and it represents less than 1/3 millionth of the total timeline. On our 24-hour cosmic clock, this journey occupies roughly 3/100ths of a second, still invisible, still a momentary flicker against the vast backdrop of cosmic time. Even the most extreme journeys we can calculate remain trivial on galactic timescales. Crossing the entire Milky Way, 100,000 light-years from edge to edge, at 1% of light speed would require approximately 10 million years. That is a genuinely long time even by cosmic standards, but it represents less than 1/10 of the galaxy's age. A civilization that launched a fleet of slow probes 10 million years ago, when our distant ancestors were small primates living in African forests, would have had enough time for those probes to traverse the entire galaxy from one side to the other. This is the reframe that changes everything. Interstellar travel is not fast. Nobody is claiming it is fast. At sublight speeds, it is grinding, tedious, and enormously slow by biological standards, but it is achievable. And the universe has provided so much time, such an incomprehensibly vast reservoir of elapsed cosmic history, that even the slowest conceivable mode of interstellar travel could have connected distant star systems many times over since the galaxy was young. Consider a specific scenario to make this concrete. Imagine a civilization that arose around a sun-like star in the Milky Way approximately 8 billion years ago, roughly 4 billion years before our sun formed. This is not an exotic assumption. As we established earlier, billions of stars with sufficient metallicity for rocky planet formation existed at that epoch. Suppose this civilization developed interstellar capability after roughly the same developmental timeline that life on Earth followed, approximately 4 billion years from the first microorganisms to a technological species. That would place their emergence as a spacefaring culture at roughly 4 billion years ago. Now suppose this civilization launched probes toward neighbouring star systems at a conservative 1% of the speed of light. The nearest target, a star perhaps 4 or 5 light-years away, would be reached in 400 to 500 years. Upon arrival, the probes survey the system, refuel or replicate using local resources, and launch the next wave toward further targets. Each hop covers a few light-years and takes a few centuries. The process repeats, leapfrogging from star to star across the galaxy. At this pace, how long would it take to visit every star system in the Milky Way? Mathematical models of this kind of diffusive expansion, published in peer-reviewed astrophysics journals, estimate that a civilization expanding at even a fraction of 1% of light speed could permeate the entire galaxy in somewhere between 10 million and 100 million years, depending on the assumptions about probe speed, replication rate, and the distribution of target systems. 100 million years sounds enormous, but remember, our hypothetical civilization launched its first probes 4 billion years ago. 100 million years is only 2.5% of the time they have had available. They could have saturated the galaxy 39 times over and still have leftover time measured in billions of years. This calculation is not original to this script. It has been made repeatedly in the scientific literature by researchers studying the Fermi paradox and the feasibility of galactic colonization. The mathematics is straightforward, the assumptions conservative, and the conclusion consistent. Any civilization with a sufficient head start in cosmic time and access to sublight propulsion technology could have explored or settled the entire Milky Way long before our solar system formed. The ancient Polynesians offer an imperfect but instructive parallel drawn from human history. Roughly 3,000 years ago, seafaring peoples from Southeast Asia began expanding across the vast Pacific Ocean using outrigger canoes and celestial navigation. They had no engines, no GPS, no satellite imagery. They sailed into an ocean covering 1/3 of the Earth's surface, navigating by stars, wave patterns, and bird flight. Their voyages between island chains covered thousands of kilometers of open water. Individual crossings took weeks. The entire expansion from island to island, generation to generation, eventually reached the remotest corners of the Pacific, including Hawaii, Easter Island, and New Zealand. They did not cross the Pacific in a single voyage. They did it in stages, island to island, generation to generation, each settlement serving as a base for the next push outward. The entire process took roughly 2,000 years, but it succeeded because the Polynesians had patience, capability, and a cultural drive to explore that persisted across dozens of generations. The distances were enormous relative to their technology. The travel times between islands were long relative to individual human lifetimes. But the expansion happened because the timescale of the project matched the timescale of the culture, not the timescale of a single voyage. Interstellar travel at sublight speeds follows precisely this same logic, scaled up to cosmic proportions. No single journey needs to span the galaxy. Each journey covers one manageable hop. A few light years, a few centuries, each destination becomes a base for the next push outward. The expansion proceeds not at the speed of a single spacecraft, but at the speed of a growing network. And given enough time, a few tens of millions of years, the network spans everything. But this brings us to a critical question that the physics of propulsion cannot answer by itself. Who or what survives a journey lasting centuries or millennia? Biological organisms age, sicken, and die. Ecosystems require constant maintenance. Societies fragment, mutate, and lose coherence across long timescales. The physics of getting from one star to another may be solved by clever engineering, but the biology of surviving the trip introduces a completely different category of challenge. A spacecraft travelling at 1% of light speed toward Tau Ceti endures a journey of approximately 1,200 years, no individual human lives that long. No known biological organism of human-scale complexity lives that long. The travellers who departed would never arrive. Their distant descendants, dozens of generations removed, would be the ones to step onto an alien world for the first time. Those descendants would have no living memory of Earth, no personal connection to the civilization that launched them, no experiential relationship with the mission's origins. They would be, in every meaningful sense, a different people. And that assumes the biological travellers survived at all. Cosmic radiation, mechanical failures, psychological deterioration across centuries of confinement, genetic drift in small populations, resource depletion, social conflict in enclosed environments with no possibility of escape or resupply. The list of failure modes for a crewed interstellar vessel on a multi-century journey is long varied, and largely unsolved by current engineering or social science. This is the biological wall that interstellar travel hits when you take the physics seriously. The propulsion problem is solvable within known physics. The survival problem is far harder, perhaps unsolvable for biological beings on the longest journeys. The stars are reachable, the journey times are finite, the speeds are achievable, but flesh and blood may not be the right medium for the crossing, unless of course you remove flesh and blood from the equation entirely. A civilization facing the reality of multi-century or multi-millennial travel times has several options for bypassing the limitations of biological lifespan. These options do not require speculative science fiction. They require extensions of engineering principles and technological concepts that already exist in embryonic form today. Generation ships that carry entire self-sustaining populations across centuries. Self-replicating probes that build copies of themselves at each destination and spread exponentially. Artificial intelligence systems that do not age, do not eat, do not suffer psychological collapse, and can be powered down for millennia and reawakened upon arrival. Robotic precursor missions that survey target systems and relay information back across the light years before any crewed vessel ever departs. Each of these strategies transforms the interstellar travel problem from a question of speed into a question of persistence. The physics of propulsion determines how long the journey takes. The engineering of survival determines what arrives at the other end. And for a civilization with millions of years of developmental time, the engineering of survival may be a solved problem in ways we cannot currently imagine. The conveyor belt of possibilities stretches outward from our solar system in every direction. Each nearby star represents a reachable node in a potential network. Each node connects to further nodes beyond it. The galaxy is not a void punctuated by unreachable islands. It is a web of destinations separated by crossable, if lengthy, gaps. The propulsion technology to begin crossing those gaps does not require new physics. It requires engineering ambition applied at scales. Our civilization has not yet attempted, but that known physical law fully permits. The distances are real. The speeds are slow, the travel times are long. But for a civilization that measures its patience in millennia rather than electoral cycles, whose planning horizons stretch across centuries rather than quarterly reports, and whose developmental history reaches back millions or billions of years before our species existed, the galaxy is not a prison. It is a neighborhood. A vast, sparsely populated, slow-to-traverse neighborhood, but a neighborhood nonetheless. One that can be explored, catalogued, and connected, star by star, century by century, probe by probe, across the patient grinding expanse of deep cosmic time. The question is no longer whether the journey is possible. The physics confirms that it is, within the constraints of sublight travel and known propulsion concepts. The question that now demands an answer is far more specific and far more consequential. What kind of traveller survives a journey measured in centuries? What kind of vessel carries life, or something like life, across the void between stars without succumbing to the 1,000 failure modes that threaten any system sustained across deep time? What technologies could bypass the fragile limitations of biology entirely and deliver intelligence, curiosity, and purpose to a distant star system after a journey lasting longer than most human civilizations have endured? That is what comes next, because the answer is not a single solution. It is a toolkit, and every tool in that kit has already been conceived, studied, and in some cases partially prototyped by human engineers working within the boundaries of confirmed physical law. If we can conceive these strategies in our technological infancy, the question of what an ancient, patient, billion-year-old civilization could engineer becomes not a matter of speculation, but a matter of scale. Biology is fragile. This is not a philosophical observation. It is an engineering constraint with specific, quantifiable parameters. Human cells accumulate radiation damage over time. DNA replication introduces errors that compound across generations. Immune systems degrade. Bones weaken in low-gravity environments. psychological resilience erodes under prolonged confinement and monotony. The human body evolved to survive roughly 70 to 80 years on the surface of a planet with a protective magnetic field, a thick atmosphere filtering ultraviolet radiation, and a gravitational pull calibrated to maintain musculoskeletal integrity. Remove any of those conditions and the biological clock accelerates toward failure. In interstellar space, all of those conditions are absent simultaneously. Cosmic radiation bombards any unshielded vessel with high-energy particles capable of shredding DNA and degrading electronic systems. The gravitational environment inside a coasting spacecraft is effectively zero unless artificial gravity is engineered through rotation or sustained acceleration. The psychological environment involves confinement in a sealed vessel for durations that dwarf any submarine deployment, any Antarctic winter-over mission, any isolation experiment ever conducted on Earth. And there is no resupply, no evacuation, no rescue. Whatever you launch with is everything you will ever have until arrival. For journeys lasting decades, these challenges are severe but potentially manageable. Humans have survived months aboard the International Space Station and emerged weakened but functional. Extending that to years or even a few decades pushes current capabilities but does not shatter them fundamentally. For journeys lasting centuries or millennia, however, biology hits a wall that no amount of exercise equipment or vitamin supplements can overcome. No human survives a 1,000-year flight to Epsilon Eridani. No crew of humans survives a 4,000-year crossing to TRAPPIST-1. The travellers who depart never arrive. Their distant descendants might, or no one might. This is the survival problem, and it is categorically different from the propulsion problem we just explored. Propulsion asks how fast you can go. Survival asks what arrives at the other end. A propulsion solution without a survival solution is a very expensive way to deliver a tomb to another star system. Any serious discussion of interstellar travel must address both questions with equal rigour. What follows are 4 strategies, each grounded in known physical principles and existing conceptual frameworks, that could solve the survival problem without requiring the travellers to be biological at all, or that redefine what biological survival means across deep time. None of these strategies has been built. All of them have been studied, modelled, and analysed by credentialed scientists and engineers working within the boundaries of confirmed physics. And for a civilization with millions or billions of years of developmental history behind it, any or all of them could represent solved problems. The first strategy is the generation ship. The concept is deceptively simple. Instead of trying to keep individual travellers alive for the entire journey, you build a vessel large enough to sustain a self-reproducing population across multiple generations. The people who launch the ship know they will never arrive. Their children will not arrive. Their grandchildren probably will not arrive either. But some generation of their descendants, dozens or hundreds of generations hence, will step off the vessel and onto a new world. The ship is not a vehicle in the conventional sense. It is a mobile habitat, a self-contained world designed to persist indefinitely while drifting between stars at whatever velocity its propulsion system can sustain. The engineering requirements for a generation ship are formidable but grounded in identifiable challenges rather than unknown physics. The vessel must maintain a closed-loop life support system capable of recycling air, water, and waste with near-perfect efficiency for centuries. Earth's biosphere performs this function effortlessly on a planetary scale, but replicating even a fraction of that capability in a sealed vessel requires extraordinarily sophisticated ecological engineering. The Biosphere 2 experiment in the early 1990s demonstrated both the potential and the difficulty. The sealed facility in Arizona struggled to maintain atmospheric oxygen levels and experienced ecological instabilities that threatened the project within its first 2 years. A generation ship would need to solve those problems permanently, with no option to open a window. The minimum population required to sustain genetic diversity across centuries of isolation has been studied by population geneticists. Estimates vary depending on assumptions about reproductive patterns, mutation rates, and the degree of genetic management the population is willing to accept. A frequently cited figure comes from a 2014 study by anthropologist Cameron Smith at Portland State University, which estimated that a founding population of at least 10,000 individuals would be needed to maintain healthy genetic diversity over multiple centuries without aggressive intervention. A smaller population of roughly 160 could theoretically survive if reproduction were carefully managed to minimize inbreeding and genetic drift, but this requires a level of social control that raises profound ethical questions about autonomy and consent across generations. The sociological challenges may ultimately prove harder than the engineering ones. A generation ship carries not just bodies but a culture. That culture must remain coherent enough to maintain the vessel, train successive generations in the technical skills needed for operation and repair, preserve the mission's purpose across centuries of transit during which the original motivation may fade into abstraction, and manage the inevitable social conflicts that arise in any closed human community. History offers few encouraging precedents. Even the most stable human institutions, religious orders, governmental structures, academic traditions, undergo radical transformation across timescales of just a few centuries. A generation ship crew departing Earth today for a 1,000-year journey would arrive as a civilization as different from the founders as modern Europeans are from the citizens of the Roman Empire at its height. NASA and various academic institutions have conducted conceptual studies of generation ship architectures. The British Interplanetary Society's Project Daedalus and its successor Project Icarus included consideration of crewed variants, though both ultimately focused on uncrewed probes for practical reasons. The 100-year Starship project, initiated in 2011 with funding from DARPA and NASA, explicitly set out to develop the capabilities needed for human interstellar travel within a century. Its research portfolio included life support systems, closed-loop agriculture, social governance models for long-duration missions, and the psychological frameworks needed to sustain crews across generational timescales. Generation ships are real concepts studied by real scientists. They are not beyond physics, they are beyond our current engineering, which is an entirely different category of obstacle. For a civilization that has had millions of years to refine closed-loop ecology, perfect genetic management, develop stable multi-generational governance, and engineer massive rotating habitats that provide artificial gravity through centripetal acceleration, the generation ship might represent not a desperate gamble, but a routine infrastructure project. A cathedral that takes centuries to build, where the architects know they will never see the completed structure but trust that their descendants will finish what they started and inhabit the result. The second strategy is radically different in character and vastly more powerful in its implications. The self-replicating probe, often called a von Neumann probe after the Hungarian-American mathematician John von Neumann, who formalized the theory of self-reproducing automata in the 1940s and 50s, von Neumann demonstrated mathematically that a machine could be designed to gather raw materials from its environment, process those materials into components, and assemble a complete functional copy of itself, including the instructions for further replication. The concept requires no biological component whatsoever. It is pure engineering, applied recursively. The application to interstellar exploration is straightforward and devastating in its implications. A civilization builds a single probe, or a small number of probes, and launches them toward nearby star systems at whatever sublight speed its propulsion technology permits. Upon arrival at a target system, the probe does not merely observe and report. It locates sources of raw material, asteroid belts, rocky moons, metallic debris fields, and begins mining. It refines ores, fabricates components, assembles copies of itself. Each copy is equipped with the same propulsion system, the same mining and fabrication capability, and the same replication instructions as the original. The copies launch toward further star systems, where the process repeats. The mathematics of exponential replication is what makes this concept so staggering. Suppose each probe takes 100 years to reach a neighboring star system at a moderate sublight velocity, and another 100 years to mine resources, fabricate copies, and launch them toward 2 new targets. That is a doubling time of 200 years. Starting from a single probe, after 200 years you have 2 probes. After 400 years, 4. After 600, 8. After 2,000 years, 1,024 probes. The growth seems slow at first, but exponential functions are deceptive. After 10,000 years, roughly 50 doublings, the number of probes exceeds 1 quadrillion. After 20,000 years, the number exceeds the total count of stars in the Milky Way. In practice, the expansion would not proceed as a perfect exponential because some target systems would lack suitable raw materials, some probes would fail, and the expanding wavefront would eventually encounter diminishing returns as nearby systems were already visited. Mathematical models published in the astrophysics literature, including a landmark analysis by physicist Frank Tipler in 1980, and subsequent refinements by researchers including Eric Jones, Robert Freitas, and others, estimate that a civilization using von Neumann probes, traveling at even a small fraction of light speed, could saturate the entire Milky Way galaxy within approximately 1 million to 100 million years. The exact figure depends on assumptions about probe speed, replication time, and the fraction of star systems that provide suitable resources. 100 million years. That is the upper bound for filling a galaxy with self-replicating machines using conservative assumptions and established science. To put that number in perspective, it represents less than 1% of the time that has elapsed since the Milky Way began forming stars. A civilization that emerged just 1 billion years ago, modest by cosmic standards, you would have had enough time to saturate the galaxy with probes 10 times over and still have 900 million years of idle history remaining. The implications are almost too large to hold in a single thought. If any civilization, anywhere in the Milky Way, ever developed and deployed von Neumann probe technology at any point during the galaxy's multi-billion-year history, their probes should be everywhere by now, in every star system, around every planet, including ours. The fact that we have not detected any such probes is one of the most profound dimensions of the Fermi paradox, and we will confront it directly before this story ends. For now, the point is narrower but essential. The technology for galaxy-wide exploration without faster-than-light travel exists in well-defined theoretical form. It requires no new physics. It requires no biological travelers. It requires only the ability to build machines that can copy themselves using available materials, a capability that is not fundamentally different from what living cells already do using molecular machinery at the nanoscale. Biology solved the self-replication problem roughly 4 billion years ago on Earth. Engineering the same capability in artificial systems is a challenge of sophistication, not of physics. Think of it as a dandelion releasing its seeds into the wind. Each seed drifts to a new location, takes root, grows into a new plant, and releases its own seeds in turn. The dandelion does not need to cross the entire field in a single leap. It spreads gradually, generation by generation, until every viable patch of soil contains a descendant. A von Neumann probe network spreads through the galaxy in precisely the same way. Slowly, patiently, inexorably. Not through speed, but through replication. Not through power, but through persistence across deep time. The third strategy eliminates biology from the equation in a different way. Rather than sending living beings or self-replicating machines, a civilization could send artificial intelligence. An AI system designed for interstellar exploration possesses a set of advantages so comprehensive that it renders biological travelers almost irrelevant by comparison. An artificial intelligence does not age. It does not require food, water, or breathable atmosphere. It does not suffer from radiation-induced cancer, or bone density loss, or muscle atrophy. It does not experience boredom, loneliness, claustrophobia, depression, or any of the psychological degradation modes that threaten human crews on long-duration missions. It can be powered down entirely during transit, consuming zero energy during the coasting phase of a journey, and reactivated upon arrival as fresh and functional as the moment it was deactivated. An AI system in hibernation mode is essentially a block of inert material drifting through space, requiring nothing, risking nothing, waiting for the moment when its sensors detect the approach of a target star and trigger reactivation. The distinction between speculative science fiction superintelligence and the kind of practical autonomous system relevant to interstellar exploration is important to maintain. We are not discussing sentient machines with human-like consciousness, existential ambitions, or emotional inner lives. We are discussing autonomous systems capable of navigating through space without real-time commands from a home planet, analyzing the environment of a target star system upon arrival, making decisions about which targets to investigate, which data to prioritize, and which signals to transmit back toward the home civilization. These capabilities represent extensions of autonomous systems that already exist in embryonic form today. NASA's Mars rovers operate with significant autonomy. Curiosity and Perseverance navigate terrain, select rock targets for analysis, and make real-time decisions about wheel placement and instrument deployment without waiting for instructions from Earth, because the communication delay between Earth and Mars ranges from 4 to 24 minutes depending on orbital positions. That level of autonomy is primitive by any advanced standard, but it demonstrates the principle. A system operating in a star system light years from home cannot wait for instructions at all. It must be fully autonomous, capable of independent operation across every contingency its designers can anticipate, and robust enough to improvise responses to those they cannot. Current trends in machine learning and autonomous systems, even extrapolated conservatively without assuming any revolutionary breakthroughs in artificial general intelligence, suggest that autonomous probes capable of interstellar mission profiles are not physically impossible. They require advances in computing, power systems, sensor technology, and decision-making software that lie well within the trajectory of current research. For a civilization with centuries or millennia of additional development time, such systems could represent mature, reliable, thoroughly tested technology deployed in vast numbers across the galaxy. An AI probe network offers a critical advantage over generation ships. It scales effortlessly. Building one generation ship is an enormous undertaking, requiring resources comparable to a small moon's worth of refined material. Building 1,000 is nearly inconceivable for a young civilization. But AI probes can be small, lightweight, and relatively inexpensive per unit. A civilization could launch thousands or millions of them, each targeted at a different star system, creating a wave of exploration that covers vast volumes of space simultaneously. The failure of any individual probe is irrelevant because the network compensates through sheer redundancy. Some probes will malfunction. Some will be destroyed by micrometeorite impacts or equipment degradation across millennia of transit. But if you launch 10,000 probes and 90% fail, you still have 1,000 successful arrivals, each one surveying a new star system and transmitting data back along the network. The fourth strategy is the most conservative and perhaps the most likely first step for any civilization contemplating interstellar exploration. Robotic precursor missions are small, relatively simple, and fast probes designed not to replicate, not to carry passengers, and not to perform complex autonomous operations, but simply to survey target star systems and relay information back to the home civilization. Think of them as the interstellar equivalent of a postal relay network. Each probe carries instruments to characterize the target system, measure the properties of any planets present, assess radiation environments, catalogue asteroid resources, and transmit its findings back toward the origin point. These precursor missions could be launched in successive waves, each generation of probes incorporating the latest technological improvements. The first wave might travel at 1% of light speed with basic instruments. By the time that wave's data returns, the home civilization has advanced further and launches a second wave at 2% of light speed with improved sensors. The second wave overtakes the first in transit or arrives at more distant targets while the first wave is still coasting toward nearer ones. Over centuries, the relay network builds outward, creating an expanding sphere of surveyed space around the home system. The information returned by precursor missions serves a crucial strategic function. It tells the home civilization which systems are worth visiting in person, or with more sophisticated probes. Which stars have rocky planets in habitable zones? Which systems have accessible asteroid belts for resource extraction? Which environments are too hostile, too barren, or too unstable to warrant further investment? This intelligence allows the civilization to allocate its more expensive assets, generation ships, AI probes, or von Neumann replicators, with precision rather than gambling on blind exploration. Robotic precursors also serve as communication relays. A probe positioned in a neighboring star system can receive transmissions from probes in systems farther out and retransmit them back toward the home system. This creates a bucket brigade communication chain that allows information to flow across distances far greater than any single transmitter could bridge. Over millennia, this relay network becomes a nervous system connecting surveyed systems across a growing volume of galactic space. The beauty of robotic precursor missions is their simplicity. They do not require the massive infrastructure of a generation ship. They do not require the sophisticated self-replication capability of a von Neumann probe. They do not require the advanced autonomy of an AI explorer. They require only the ability to build a durable spacecraft, point it at a star, and give it instruments sensitive enough to characterize what it finds when it arrives. This is the lowest rung on the interstellar technology ladder, the first step that any spacefaring civilization could plausibly take with relatively modest resources. Now synthesize all four strategies and consider what a civilization with millions of years of developmental time could accomplish by deploying them in combination. This is not a matter of choosing one approach and hoping it works. A sufficiently old and capable civilization could deploy all four simultaneously, each serving a distinct function within a unified exploration architecture. Robotic precursors go first. Small, fast, cheap, launched in waves of thousands toward every promising star system within a growing radius. They survey, characterize, and report back, building a map of the galactic neighborhood that grows more detailed with each successive wave. This is the scouting phase. Von Neumann probes follow. Targeted at systems the precursors identified as resource-rich, these self-replicating machines establish mining and manufacturing infrastructure at each destination. They build copies of themselves and launch those copies onward, expanding the network exponentially. They also construct communication relay stations, power generation facilities, and raw material stockpiles that future arrivals can use. This is the infrastructure phase. AI-driven explorers come next. More sophisticated than the precursors, these autonomous systems conduct detailed scientific investigation of each system. They analyze planetary atmospheres, study geological activity, search for biosignatures, catalog resources with precision, and make independent decisions about which findings warrant priority communication back to the home civilization. They operate independently for centuries or millennia, maintaining the network and updating the galactic map continuously. This is the intelligence phase. Generation ships arrive last, if they arrive at all. Targeted only at systems the previous three phases have confirmed. As suitable for habitation, these massive vessels carry biological populations to worlds that have already been surveyed, mapped, and prepared. The colonists arrive not in unknown territory, but in systems where robotic infrastructure is already in place, where resources have been identified and stockpiled, where communication links back to the home civilization are established and operational. This is the settlement phase. Think of this four-phase architecture as a Swiss Army knife for galactic exploration. Each tool serves a specific purpose. Each compensates for the limitations of the others. Precursors lack the ability to build infrastructure, but von Neumann probes provide it. Von Neumann probes lack sophisticated analytical capability, but AI explorers supply it. AI explorers lack the cultural continuity and biological adaptability of living populations, but generation ships carry them. No single strategy needs to be perfect. The system works because the strategies complement each other, and because the timescales involved allow for failure, iteration, and refinement across millions of years. And here is the critical point that ties everything back to the cosmic timeline we began with. None of these technologies demand a single discovery beyond our current understanding of how the universe works. Generation ships require closed-loop ecology and social engineering across centuries. Von Neumann probes require self-replicating machine technology. AI explorers require advanced autonomous systems. Robotic precursors require durable spacecraft with good instruments. Every item on that list is a problem of sophistication, scale, and patience. Difficult? Yes. Forbidden by the laws of nature? No. We, a civilization barely 2 centuries into the industrial age, can already identify these strategies, model their feasibility, calculate their expansion rates, and begin preliminary work on their component technologies. Breakthrough Starshot is designing laser-propelled probes. NASA is advancing autonomous navigation systems. Researchers are studying closed-loop life support for deep space habitats. The theoretical foundations for self-replicating machines were laid down over 70 years ago by one of the greatest mathematicians in history. If we can conceive these strategies in our technological infancy, then a civilization with a million-year head start has had time to move from conception to prototype to deployment to galactic-scale operation and back again, thousands of times over. A civilization with a billion-year head start has had time to refine these technologies through more iterations than we can meaningfully count. The engineering challenges that feel overwhelming to us might represent solved problems that an ancient civilization deployed so long ago that their probe networks have been operating autonomously for longer than complex life has existed. On Earth, the tools are defined. Not one of them asks the universe to bend its rules. The timescales of cosmic history accommodate their deployment with room to spare that dwarfs the entire existence of our species. The galaxy is navigable not through speed, but through redundancy, replication, autonomy, and the patient accumulation of infrastructure across deep cosmic time. A single chapter in the history of a billion-year-old civilization would be more than sufficient to saturate the Milky Way with probes, relay stations, and surveyed systems from core to rim. Which brings us to the question that has been building throughout this entire story. The question that transforms intellectual curiosity into genuine unease. The question that physicists, astrobiologists, and philosophers have been debating since Enrico Fermi first asked it over a lunch table at Los Alamos in 1950. The universe is old enough. The planets are numerous enough. The distances are crossable. The technologies are conceivable. The timescales are sufficient by many orders of magnitude. Everything in the physics, the chemistry, the biology, and the engineering points toward the same conclusion. Interstellar travel by sublight probes or vessels, expanding outward from even a single origin point, could have filled the galaxy with evidence of intelligence many times over during the billions of years before Earth existed. So where is everybody? Why is the evidence locker empty? Why has the most sensitive detection equipment our species has ever built found nothing? No signals, no probes, no artifacts, no megastructures, no signatures of any kind, from any civilization, anywhere in our galaxy. That silence is the most profound mystery in science, and confronting it honestly, without retreating into comfortable certainties or unfounded speculation, is what comes next. In the summer of 1950, at Los Alamos National Laboratory in New Mexico, 4 physicists sat down for lunch. Enrico Fermi, Edward Teller, Herbert York, and Emil Konopinski had been discussing a recent New Yorker magazine cartoon depicting aliens carrying trash cans stolen from New York City streets. The conversation drifted from the cartoon to flying saucer reports that had been circulating in the popular press, and then naturally toward a more serious question. Given the age of the galaxy, the abundance of stars, and the apparent feasibility of interstellar travel even at sublight speeds, Surely at least one advanced civilization should have visited or colonized the galaxy by now. The logic seemed airtight. The numbers pointed overwhelmingly toward contact, and yet the evidence was absent. In the middle of the conversation, without preamble or build-up, Fermi looked up from his lunch and asked the question that has haunted astrophysics ever since. Where is everybody? The question was casual in delivery and devastating in implication. Fermi was not asking whether aliens existed in the abstract philosophical sense. He was pointing out a specific mathematical contradiction. If civilizations arise with any reasonable frequency among the billions of habitable worlds in the galaxy, and if even one of those civilizations developed interstellar travel capability at any point during the galaxy's multi-billion-year history, the exponential logic of expansion should have filled the galaxy with evidence long ago. Probes in every system, signals saturating the electromagnetic spectrum, megastructures visible through telescopes, artifacts on planetary surfaces, something, anything. The math demands it. Yet the sky is silent. The solar system appears untouched. No artifact, no signal, no structure attributable to extraterrestrial intelligence has ever been confirmed by the scientific community. This contradiction between expectation and observation is the Fermi paradox, and it is not a minor puzzle to be filed away alongside other unsolved questions in astronomy. It strikes directly at the intersection of everything we have explored in this story. The ancient age of the universe suggests that civilizations had billions of years to emerge before us. The crossable distances and achievable speeds we calculated demonstrate that interstellar travel does not require physics beyond what we already understand. The technological strategies we explored show that biology is not a limiting factor when machines can carry the mission forward across millennia. Every thread of evidence and logic points toward a galaxy that should be teeming with the traces of intelligence. Every observation we have made points toward a galaxy that is, as far as we can tell, completely empty of such traces. That tension is not resolved. It is the central mystery of astrobiology, and anyone who claims to have a definitive answer is either overstating their case or not understanding the question. What we can do is examine the most scientifically grounded proposed resolutions and evaluate what each one implies about our place in the cosmos. None of these resolutions is confirmed. All of them are speculative to varying degrees, but each one illuminates a different facet of the paradox and forces us to confront different uncomfortable possibilities. The first and perhaps most sobering resolution is the rare Earth hypothesis. Proposed formally by geologist Peter Ward and astronomer Donald Brownlee in their 2000 publication of the same name, this hypothesis argues that while microbial life may be relatively common throughout the galaxy, complex multicellular life, and especially intelligent technological life, may be extraordinarily rare. The argument does not dispute that habitable zone planets exist in abundance. It disputes the assumption that habitable conditions automatically produce complex organisms. Earth's journey from the first single-celled organisms to a civilization capable of detecting exoplanets required an improbable sequence of events. The stabilizing influence of a large moon that regulates axial tilt, the protective magnetic field generated by a liquid iron core, plate tectonics recycling carbon, and maintaining atmospheric equilibrium over billions of years, a gas giant positioned in the outer solar system deflecting cometary bombardment that might otherwise sterilize the inner planets, mass extinction events that cleared ecological niches and enabled new evolutionary trajectories. Each of these factors may be necessary for the emergence of complex life, and the probability of all of them occurring together on a single world may be vanishingly small. If the rare Earth hypothesis is correct, the galaxy could contain billions of planets with microbial life, but virtually none with intelligent civilizations capable of interstellar travel. We would not be merely early arrivals at the galactic party. We might be among the only guests who will ever attend. The silence would not be a paradox at all, but simply the expected state of an overwhelmingly microbial galaxy, where complex intelligence is a statistical anomaly verging on uniqueness. The second resolution invokes a concept that is both more dramatic and more disturbing. The Great Filter, a term coined by economist Robin Hanson in 1998, proposes that somewhere along the chain from dead chemistry to spacefaring civilization, there exists a barrier so difficult to cross that virtually no lineage ever makes it through. The critical question is whether that filter lies behind us or ahead of us. If the Great Filter is behind us, meaning it corresponds to a step that Earth has already successfully passed, then we are among the rare winners of a cosmic lottery. Perhaps the origin of life itself is the filter. Perhaps the transition from prokaryotic to eukaryotic cells, which took roughly 2 billion years on Earth, is the bottleneck. Perhaps the emergence of multicellular life or the evolution of intelligence represents the improbable step. In any of these cases, the galaxy is filled with worlds where the chain stopped short, where chemistry never became biology, or biology never became complex, or complexity never became intelligent. Our existence would be exceptional, and the silence would be the sound of an empty galaxy in which we are among the vanishingly few who made it through. If the Great Filter lies ahead of us, the implications darken considerably. This would mean that civilizations arise with some regularity across the galaxy, but consistently destroy themselves before achieving interstellar capability or shortly thereafter. Nuclear war, engineered pandemics, artificial intelligence catastrophe, climate collapse, resource exhaustion, ecological overshoot. The mechanisms vary, but the outcome is the same. Civilizations burn brightly for a few centuries or millennia, and then extinguish themselves before they can spread beyond their home system. The galaxy is not empty because life is rare. It is empty because intelligence is self-terminating. The silence is the sound of 1,000 civilizations that reached for the stars and fell back into the dark. Which scenario is correct carries existential weight for our own species. Every time we discover that a supposedly difficult evolutionary step was actually commonplace, it shifts the likely position of the Great Filter from behind us to ahead of us. If life arises easily, that is bad news. It means the filter is not the origin of life. If complex multicellular life is common, that is worse news. It pushes the filter further toward our future. The discovery of microbial life on Mars or Europa would be the worst news of all in this framework, because it would suggest that every step up to complex life is easy, meaning the filter that stops civilizations from filling the galaxy must lie somewhere in our future. The third category of resolutions does not argue that civilizations are rare or self-destructive. It argues that they exist, but choose not to expand, or at least not in ways we can detect. The zoo hypothesis, proposed by astronomer John Ball in 1973, suggests that advanced civilizations are aware of us but deliberately avoid contact, treating Earth as a nature reserve or a sociological experiment to be observed without interference. This is an appealing idea because it preserves the existence of alien intelligence while explaining the silence, but it suffers from a serious logical weakness. It requires every civilization in the galaxy, without exception, to independently adopt the same non-interference policy. Even one defector, one species that disagreed with the consensus, would shatter the zoo, and across billions of years and potentially thousands of independent civilizations, unanimity seems implausible. The dark forest hypothesis, popularized by science fiction author Liu Cixin in his novel of the same name but rooted in game theoretic reasoning, proposes a grimmer version. In a galaxy where civilizations cannot verify each other's intentions across interstellar distances, the safest strategy is to remain silent and hidden. Any civilization that reveals itself risks annihilation by a more powerful neighbor operating under the same logic. The galaxy becomes a dark forest full of armed hunters, each one silent, each one listening, each one ready to strike at the first sign of another presence. Under this hypothesis, the silence is not evidence of absence, but evidence of universal caution. Everyone is hiding because revealing yourself is suicidal. The dark forest model is intellectually coherent, but unfalsifiable with current data. We cannot determine whether civilizations are hiding from observation because successfully hidden civilizations are by definition undetectable. It also requires that offensive capability consistently exceeds defensive capability across all technological levels, which is an assumption about alien engineering. We have no way to evaluate. A fourth resolution is less dramatic but potentially more scientifically significant. Perhaps the galaxy is partially explored or settled, but the distances and timescales involved mean that contact between settled regions and unsettled regions is simply unlikely during any given millennium. The Milky Way is 100,000 light-years across. Even with von Neumann probe networks expanding at a fraction of light speed, the galaxy is enormous. There could be pockets of civilizational activity scattered across the disk, separated by thousands of light-years of unsurveyed space, with exploration wavefronts that have not yet reached our neighborhood. We might be sitting in an unvisited region not because the galaxy is empty, but because the visitors have not arrived yet. Given the timescales involved, the difference between never arriving and not yet arriving is indistinguishable from our current vantage point. There is also a resolution that deserves serious consideration precisely because it challenges an assumption we rarely question. Perhaps evidence of extraterrestrial intelligence does exist within our solar system or within our detection range, but we have not recognized it because we do not know what to look for. A von Neumann probe that arrived in our solar system millions of years ago might be sitting on an asteroid or orbiting in the outer solar system in a dormant state, indistinguishable from a natural object without close physical examination. A signal transmitted at a frequency or using a modulation scheme outside our current detection parameters would pass through our instruments without triggering any alert. We assume we would recognize alien technology if we saw it, but this assumption rests on the belief that we can anticipate the engineering choices of a civilization potentially millions or billions of years more advanced than ours. That belief has no empirical foundation. This leads directly to the most important and most frequently overlooked dimension of the Fermi paradox: the scale of what we have actually searched versus the scale of what remains unsearched. And the numbers here are humbling in a way that reframes the entire conversation. The SETI program, the search for extraterrestrial intelligence, has been operating in various forms since Frank Drake conducted the first systematic radio search in 1960, Project Ozma, which targeted 2 nearby stars using a single radio frequency. In the 65 years since, SETI has expanded dramatically. Modern programs like the Breakthrough Listen initiative use sophisticated multi-channel receivers monitoring billions of frequencies simultaneously across thousands of target stars. The Allen Telescope Array, the Green Bank Telescope, the Parkes Radio Telescope, and other instruments have contributed to an accumulating dataset of radio and optical observations specifically designed to detect artificial signals. This sounds comprehensive. It is not even remotely. A frequently cited analogy in the SETI community compares the search effort to date with the task of determining whether Earth's oceans contain fish by scooping up a single cup of water and examining it. The volume of electromagnetic search space that SETI has actually sampled, accounting for the number of stars observed, the range of frequencies monitored, the sensitivity thresholds applied, and the fraction of observing time dedicated to each target, represents an almost infinitesimally small fraction of the total parameter space that would need to be covered for a comprehensive search. A 2018 study led by astronomer Jason Wright and colleagues at Penn State calculated the fraction of the galaxy's communication volume that SETI had effectively searched. Their conclusion was striking. After nearly 6 decades of searching, humanity had sampled the equivalent of a hot tub's worth of water from an ocean the size of Earth's combined seas. The search had been conducted with real instruments producing real data, but the coverage was so sparse that the absence of a detected signal carried almost no statistical weight. You cannot conclude that the ocean is empty of fish based on a single cup of water, and you cannot conclude that the galaxy is empty of signals based on 6 decades of narrow, intermittent, geographically limited searching. This framing transforms the Fermi paradox from a statement about alien absence into a statement about human limitations. We have not found evidence of extraterrestrial intelligence. That is a fact. But we have searched so little of the relevant parameter space that the absence of a detection is statistically meaningless. It would be extraordinary if we had found something, given how little we have looked. The paradox is real as a logical tension, but the evidentiary weight of our non-detection is far lighter than popular discussions typically acknowledge. Our own electromagnetic footprint illustrates the detection challenge from the opposite direction. Humanity has been broadcasting radio signals into space for roughly 120 years, since Marconi's first experiments in the early 1900s. Those signals expand outward at the speed of light, forming a thin shell of detectable radiation centered on Earth. That shell currently has a radius of approximately 120 light-years. It encompasses roughly the nearest several 100,000 stars. But 120 light-years is a tiny bubble within a galaxy, 100,000 light-years across. Our radio shell has reached less than 0.2% of the Milky Way's diameter. A civilization on the far side of the galaxy would not receive our earliest signals for another 99,880 years. Assuming those signals remain detectable at such distances, which they almost certainly would not. Our television broadcasts and radar emissions attenuate with the square of distance, becoming indistinguishable from background noise within a few light years without an impossibly large receiving antenna on the other end. We are electromagnetic infants. We have been broadcasting for an eye blink on cosmic timescales, and our signals are detectable only within a minuscule bubble of local space. If an alien civilization operates under similar constraints, their signals might be undetectable from our position regardless of how powerful their transmitters are. The galaxy could be buzzing with communication, and we would hear nothing because the signals have not reached us, have faded below our detection threshold, or use technologies and frequencies we are not monitoring. Now we arrive at the distinction that matters more than any other in this entire story. The difference between possible and likely. Because everything discussed throughout this story is possible. Not one claim made in this story asks the universe to behave differently than we have measured it behaving, contradicts confirmed observations, or requires technology beyond the plausible engineering horizon of an advanced civilization. Interstellar travel at sublight speeds is possible. Generation ships are possible. Von Neumann probes are possible. AI-driven exploration is possible. Galaxy-wide expansion over tens of millions of years is possible. All of it fits within the confirmed framework of physics, chemistry, and mathematics that governs our universe. But possible is not the same as likely, and likely is not the same as actual. The space between what physics permits and what reality contains is vast, and we have no way to bridge that space without evidence. We do not know whether life is common or rare. We do not know whether intelligence arises frequently or almost never. We do not know whether civilizations tend to expand or tend to collapse. We do not know whether the galaxy contains 1 million species of intelligent life or exactly one. Every number in the probability chain, from the fraction of habitable planets that develop life to the fraction of civilizations that survive long enough to build interstellar probes, remains unmeasured. We are estimating the probability of a chain of events for which we possess exactly one data point, ourselves, and a sample size of 1 supports essentially any conclusion you want to draw. This is not a failure of science. It is the honest position of science given the current state of evidence. We know the universe is old. We know habitable planets are common. We know sublight interstellar travel is permitted by physics. We know that technologies for long-duration space exploration exist in well-defined conceptual form. We know that the timescales of the universe are sufficient for slow probes to have crossed the galaxy many times over. And we know that despite all of this, we have detected nothing. Both of the competing conclusions remain equally valid in the absence of further data. Conclusion 1. Civilizations are so rare, or so consistently self-destructive, or so disinclined to expand, that none has ever launched a probe in our direction, and the galaxy is effectively empty of interstellar travelers. Conclusion 2. Civilizations have launched probes or vessels, some of them potentially millions of years ago, and those travelers are out there in the void right now, drifting between stars at a fraction of light speed, following trajectories set in motion before our species existed, approaching destinations they may not reach for centuries or millennia yet to come. We cannot distinguish between these conclusions with the tools and data we currently possess. Anyone who tells you with certainty that aliens are coming is not doing science. Anyone who tells you with certainty that they are not is making the same mistake in the opposite direction. The honest answer, the scientifically rigorous answer, is that we do not know. We lack the evidence to resolve the question. And that uncertainty, that genuine not knowing, is the most important thing to sit with as this story reaches its conclusion. Because uncertainty is not emptiness. It is loaded. It carries the full weight of everything we have discussed. The 13.8 billion years of cosmic time that preceded our arrival. The billions of habitable worlds orbiting stars far older than our Sun. The finite crossable distances between neighbouring star systems. The propulsion concepts that require no new physics. The self-replicating machines. The AI explorers. The generation ships. The robotic precursors that could carry intelligence across the void without requiring biological survival. The mathematical models showing that a single civilization could saturate the galaxy with probes within a time frame that is negligible compared to the age of the Milky Way. All of this sits inside the uncertainty. All of it is real, confirmed, grounded in observation and calculation. The only missing piece is the one piece that matters most. Has anyone ever actually done it? Imagine standing alone in a vast dark room. You hold a single candle. Its light reaches perhaps 10 feet in every direction, revealing bare floor, empty air, silence. Beyond the candlelight is darkness extending in every direction farther than you can perceive. You have been standing here for 65 years, which is how long humanity has been conducting any form of systematic search for extraterrestrial intelligence. And in those 65 years, your candle has illuminated a tiny sphere of the room and found nothing. Can you conclude the room is empty? Of course not. Your candle lights a fraction of the total volume. Something could be standing 50 feet away, completely invisible to you, waiting, dormant, utterly silent. Or the room could be genuinely empty, and your search will never find what was never there. Both options are consistent with what your candle shows you. The darkness does not resolve the question. It preserves it. That is where humanity stands right now. Our instruments are the candle, the galaxy is the room, and the darkness is not an answer. It is the space where answers have not yet been found. The universe does not owe us company. It does not owe us evidence. It does not owe us resolution to the tension between what physics permits and what observation confirms. The cosmos is under no obligation to be populated, to be communicative, or to be comprehensible to a species that has been looking for answers for less than a century within a story that has been unfolding for nearly 14 billion years. We are newcomers making our first tentative observations and demanding that the universe explain itself on our schedule. It will not. But what the universe has given us is something more valuable than an answer. It has given us a question worth asking. A question that is grounded not in fantasy or wishful thinking, but in the confirmed realities of astrophysics, planetary science, and engineering. The universe is old enough for slow travellers to have crossed it many times. The galaxy contains enough habitable worlds to provide both origins and destinations in staggering abundance. The technologies for interstellar travel at sublight speeds exist in theoretical form and violate no known physical law. The timescales required for galaxy-wide exploration are trivially short compared to the age of the cosmos. Something could be on its way. A von Neumann probe launched by a civilization that flourished and faded 100 million years ago, still drifting on its original trajectory, still carrying its replication instructions, still following its programming across the silent void between stars. An AI explorer, powered down, coasting through interstellar space at 3% of light speed, its sensors dormant, its mission clock ticking toward a reactivation date still centuries in the future. A generation ship, its original builders long dead, its current inhabitants, the 50th generation of a culture that has forgotten what the origin world looked like, approaching a star system that their ancestors selected from a catalogue compiled before Earth's dinosaurs went extinct, or nothing could be on its way. Every civilization that ever arose could have destroyed itself before reaching the stars. Life could be so rare that we are functionally alone in the Milky Way. The Great Filter could be behind us, making our existence a cosmic miracle. The galaxy could be exactly as empty as it appears, and the silence could be the simple, stark truth of a universe where intelligence is an accident that almost never happens and never persists. Both of these possibilities are real. Both are consistent with everything we know. Both deserve to be held simultaneously, without collapsing into premature certainty in either direction. The intellectual tension between them is not a flaw in our understanding. It is the most honest reflection of where our understanding currently stands. The cosmos is old enough and vast enough to accommodate travelers we have never detected. It is also cold enough and silent enough to suggest that perhaps no traveler has ever set out. We sit at the intersection of these two truths, a young species on a small planet, holding our single candle in a very dark room, listening to a silence that could mean anything. Somewhere out there, beyond the reach of our telescopes, beyond the thin shell of our radio transmissions, beyond the small sphere of space our instruments have surveyed in 6 decades of searching, the galaxy continues. 400 billion stars burn steadily in the dark. Tens of billions of rocky planets orbit in habitable zones, some of them billions of years older than Earth. The distances between those worlds are vast but finite. The travel times are long but achievable. The technologies are demanding but physically permitted. The question is not whether the journey is possible. We have spent this entire story demonstrating that it is. The question is whether anyone has ever begun it, and to that question, we have no answer. Only the silence, only the scale, only the profound, unresolved tension of a universe that seems built to accommodate travelers but has not yet shown us a single one. That silence is not the end of the story. It is the beginning. It is the reason we build bigger telescopes, develop more sensitive detectors, launch missions to survey nearby exoplanets, and continue the search that began with Frank Drake pointing a radio telescope at 2 stars in 1960. Every improvement in our instruments slightly enlarges the candle's glow. Every new exoplanet discovered adds another dot to the map. Every year that passes without a detection narrows the possibilities by the smallest of fractions, while leaving the deepest questions entirely intact. We are looking. We are listening. And the universe, ancient and vast and patient beyond all human comprehension, keeps its counsel. For now.